Okay. Perfect. Hello, everyone. In today's short session, what I wanted to do was to study a bit, continue the study of Laplace expansion that we've done last week. Hey, hi, how are you? That we did last week. You can follow along if you want to. I'm mainly going to be in this website, DeepML. Pretty cool website. They keep improving it. There's a lot of problems that you can like play around with, and I really like the linear algebra ones. I've been going at them for a few months now. So yeah, you can check it out. It's pretty cool. We're gonna also use this book, The Mathematics for Deep Learning, just the section 4 with the determinant and trace. So hey, how are you? So yeah, so that's pretty much it. The formula for Laplace expansion shouldn't be too hard to compute. It's a bit of a recursive function, and then there's positional information that we need to make sure that we pass through. So we're gonna break this down and then go at it. What is the link between like this thing and deep learning in general? It's pretty much having to do with like a singular value decomposition, like eigenvalues and eigenvectors, and PCAs. Like everything having to do with like dimension reduction, the determinant and / the eigenvalues, eigenvectors are pretty important for that. You'll most likely never going to be at the level where you have to understand how the determinant is how to say it, like calculated whenever you're going to do like deep learning in practice. But it's useful to understand at the deep level these more fundamental components, because it shows you how things are moving around, and how like get you an intuition about what's going on when you're doing a bunch of manipulations. So that's it. So like always with these live stream, like don't hesitate to ask me absolutely any question that you have in terms of deep learning, machine learning. I'll try to be as helpful as possible. So let's get this started. I'm just gonna collect a bunch of information here. So yeah, this first point here, okay, let's go with that. The formula is this. No, I didn't. I didn't watch Gilbert Strang lecture. Can you link them here? That would be useful. It's on what? It's on the linear algebra. Okay, I'm just gonna make a new page here. Okay, so this is that, and do I need something else? I think that's it. That's all I need here. Do I need something else? No, I think that's good. There's multiple, well, I need that too. Yeah, this over here. I can either go, is it gonna be a 3x3? There's two ways of going about that. Because in our case, we're gonna be, if we look at the problem set here, it's doing a determinant of a 4x4 matrix using Laplace expansion. Okay, cool. We'll check it out afterward. So a 4x4, the issue with it, if you remember how the determinants are calculated, right? So you have like 1, 2, 3, 4, and then like this continue 7, 8, 12, 13, 14, 15, and 16. Okay. So we have a whole bunch of them. So if we're gonna calculate this, and like you can follow this formula, but it's basically recursive, meaning that like you have to select either the row or column, and then you're gonna go either way. And if you select, let's say, the row, and you're going to go like this, what you're going to need to do is you're going to need to do this, and then you take the variable, so that one, and then you kind of eliminate whatever is in the column. So j equal 0, you're going to eliminate it, and then I equals 0, you're going to eliminate it too, right? In order to capture that thing, right, this little grid over here, and that grid will become the thing that you need to find your determinant on. And then you're going to do like either plus or minus. So there's also a motion here where it's going to be either plus or minuses depending on your position on this grid. So the formula to find if it's a plus or a minus is this, right? This little bit here is the thing that will tell you that. So that part is not too difficult. So to understand when you're gonna have to put a plus or minus, it's not too bad. If we put it here, there's a pattern that you can kind of know about. There's a plus here, and then you're gonna create some minuses here, right? There's a plus here, you're gonna create a minus, plus over here, a minus there, plus, minus, and a plus here. And then it will continue that pattern over and over again. You can get it with this, with the K and the J here. They're using J as, okay, it just doesn't matter which one is which. K is a column, and then K or J are column, and then it's interchangeable here. So you're using in our case, it's going to be J and I, and this will tell us if we're going to put the plus here or a minus, and then you do the rest over here. So we're going to have this whole thing can be encoded into -1, and then K plus J here. So this is the row, right? And this is our column over here, right? So that thing, and then like we're gonna do this times, right, the rest of this thing, this motion that we have here. There's a motion that is happening here where we're gonna slice the stuff. I don't think it's that difficult to do. If we already have the how is the matrix encoded? It's list of lists. Okay, yeah. A list of lists will be a bit of a pain, because we need to recreate it every time. The list of list thing, I think it's gonna be fine. No, it's gonna be good. We're gonna need to have something in there to eliminate, right? So some sub-function to eliminate rows and column by indexing properly, right? And then you get that there. And then once we are gonna iterate over a row, there's gonna be like a main loop here, right? So in there's gonna be a main loop that will iterate. Let's go rows over rows. So that's that. And then we have two choices. We have two choices. Either here we're gonna go. There's two ways of going about this, right? Remember with I'm gonna fetch it from here. There's the Cyrus rule that we can use. So this one here, right? It's either going to be this one or this one. So what I'm saying here is that at some point you have to calculate the determinant of something with this motion, right? You can't just like go on forever. At some point you have to stop and actually do some computation. So there's two things that we could do. Either we have, let's say, a 2 by 2, and then you're gonna do the motion that is like this times this minus this times this, right? So this is that formula over here. Or you can stop at the 3 by 3 and do like the motion that is like that. It's like this, and then this, and then this, minus like that, plus that, plus that, right? It's easier to see if you increase the number of columns that you have. But that's the one, right? It's a bit more bulky. I'll go with this one first, right? And after that, we can maybe like continue the recursion and go for the 2 by 2. But it will be the same same type of flow. Yeah. So okay, main loop, and then here at some point where I need to calculate. Let's put it here. At some point, calculate the 3 by 3, and that's pretty much that. There's not that much complication here. The 3 by 3 is easy. You're just gonna calculate it. I can just hard code it literally based on the position of these elements. Yeah. Okay, cool. Perfect. I'll get to it. So I'll first get another determinant of a 3 by 3, right? I'm gonna take a matrix, list of list, int or float here, and then we're gonna return a float. Do you see well now? Right, sorry. Can I put that? Yeah, full screen. Okay, and I'm just gonna put myself. Okay, should be good. Then this return the float. Okay, pass. Here we are. Rule directly. Okay, so if you remember the Cyrus rule here, it looked like this. So the main diagonal, and then we're gonna go. I'm gonna do it one by one here. So we're gonna have matrix. So this is the rows. The first one will be the rows, and then after that will be the column, I believe. Is that this? Yeah. This is first row, second row. Okay. So this is the ID for the rows. So 0, 0. So this is a 1, 1. And then we're going to do this plus 8, 2, 2. One. Actually, it's not plus, it's multiplied. Two. Okay. I'll just gonna label them. Yeah, for now I'll just label them. Okay, green 1. And then we're gonna have the green 2. Matrix. It's a bit difficult in terms of like 2, 1. 2, 1 is what? So it's these one, 2, 1, 3, 2, and then 1, 3. So 2, 1. So we're in the second row, and then first column times the third row, second column. So third row, second columns times first row, last column. Right. So that's over there. It's 1, 2, 1, 3, 2, 1, 3. Okay, getting there. So last one is this bit over here. So 3, 1, right? So matrix 2 and 0 times matrix at, now it's like this part over here, 1, 2 and 2, 3. So 1, 2, this is the first row and the second column. So this, we are getting there. And the last one is this. So it's the second row. So 2 like this, and last column 2. Oof. Okay, so A is 3, 1 times A 1, 2 times A 2, 3. Is that right? Yeah, perfect. That's the greens, and then we're gonna do the reds. Red one. Right. For those that are not maybe too familiar, like it's this motion here, just like this slashing that we're doing, right? Like this, and then like that over here. Sorry, this one, and here. And now we're doing the reds. I'm actually gonna remove this because I can't see shit. Okay, so the reds is starting with these over here. So no, wait, yeah, it's, oh, they're doing it like this. Okay, so it's the same thing. So it's the main diagonal but on the other side. So matrix 2, 0, and then we have matrix so this is gonna be, so this is 2, 0, this is 1, 1, 1, and then here this is gonna be 0, 2, right? Then we have red 2. So this one is done, and we have 1, 1, 3, 2. Okay, this one over here, 3, 2, and then this one. So okay, 0, 0 times matrix 2, 1 times matrix 1, 2. Okay, and then the last red, okay, the last red is which one is it? 2, 1, 1, 2, and then this one over here. So 2, 1. That's 2, 1, right? So 2, 1 first. Yeah. Okay, and this one is 0, 1. It's very easy to get absolutely fucking lost in this thing. Like usually in these implementation, the main bugs you're gonna see are these. So let's double check. So this is A 3, 1 times A 2, 2 times A 1, 3. Is this good? 2, 1. Yeah, this is good. And then this one is A 1 times A 3, 2 times A 2, 3, right? That's good. Yes, it's good. And then our very last one is going to be A21, A12, A33. Okay, perfect. So we got these right. We got these right fully. And then we just need to calculate the determinant. So the determinant is going to be equal to the greens 1 plus green 2, green 3, minus red 1, red 2, red 3. That's roughly it. Yeah, it's just that. There's nothing too complicated. And we're gonna return that. Okay. Perfect. So that's the first bit that we got out of the way. Yes. So if we go back to this, this is good. So we're able to calculate this, right? So every time we're going to calculate in our recursive function, this det is going to be det 3 by 3, right? And it will go into our setup, which we think is going to be fine if we didn't mess it up. So we just need to construct this properly. And the next thing I'm going to do is I'm going to construct a loop that's going to go like this. And I'm going to get me like with, how is it this one called? I think it's called a cofactor. What's it called? Is it the, no, it's this one is the cofactor. So there's no, I don't even know like what's the name of like this, let's say this matrix, but this matrix that is going to give us the sign that we're going to have to multiply this element here. This is the second thing that we need to get right as we go through this row. So in this case, we're just going to go for, here we just have to be careful. I'm going to use the same, they use what? I and J, I'm going to use I and J. So I is the row, and for row I in range, and then we're going to go length matrix. That will give us our first thing here, right? So here we're iterating over the rows. So if we are iterating over the rows, there's a few things that we need to do. First is get our, how do they call this? How do they call the, this element? I'm just going to call it a scalar, I guess. Is there... I don't know. It's just an element. It doesn't have a name. Okay. I'm going to call it the scalar. So we get our scalar here. And we're going to go with the... we're going to go with the first row here. And then just iterate over the row. So this ID will be for only the first row. And our column will be stuck at 0. That's no, or no, wait, the, oh, depends. If I go like this with the rows, I'm just gonna go like this. It works also, like it doesn't matter here. It's gonna be the row that will stay, right? Well, the row will stay at 0. And it's going to be the column that will be moving. It's going to move like this. So if I do it like that. It kind of doesn't matter, I guess. Yeah, I don't think it matters too much. Okay, well, it doesn't matter too much. So we're gonna get our element. So here, get our scalar, And to do that, I'm going to do matrix. It's going to increase that, sorry. Matrix at 0, and then our, well, row I, and we're going to jam this at 0. And that's going to be our A. So I'm just going to call it scalar here, right? And then we're going to get our, wait, how do I do that? Sorry. That times mat.pow, and then I want to do the value of this raised to row I plus 0, because this one stays at 0, right? That's the right way to do it. So here at 0, 0 is going to be minus 1, 0, that's going to give us a 1, right? And then here, after that, it's going to do minus 1, and then a 0 plus 1, sorry, 1 plus 0, that's going to give us a minus 1. Perfect. We don't have to add the zeros, but I'll just add it anyway. And then here is going to be our multiplication. So our sign multiplier, right? And then it's going to be scalar times sign multiplier to get our stuff that we need. And we should be good with that. Yeah, we should be good with that. So we're going to get that. We currently have that part down, right? That part is done. We just need to recursively like cut it out. And it's going to be scalar get multiplier here, and the last thing is get slice or matrix to get the sub 3 by 3 matrix. And here we're gonna have to slice it. The 0 stays the same. The column doesn't change. It's going to be the rest that will change. Can I index into that? Wait. Indexing into 2D array. I don't think I can index like this. No. I can create a NumPy array though. That would be much easier if I do it like that. Yeah. Yeah, I think I'm just gonna jam this into setup our list of list as a 2D NumPy array. So I think it's just like NP array, and then we give our matrix. And then the matrix will be this. So at this point, I can slice it like this, and I can slice that. And just take the matrix at the right spot. Yeah, I think I can just delete, right? Delete NumPy row and column from matrix. Yeah, I think that's this. Yeah, I think I can do it like that. NP delete. Yeah, I think that's this. Okay, so we have the array, the object slice int array like of integer bool, and then the axis. So if I want to, I think it's preferable to use a Boolean mask, for example, that, okay. Okay, what is it? What are they even doing here? Okay, so we have that, and then what they're doing here is they're deleting this middle one along this axis. So this is the axis. Okay, I can just do two of them, right? I'll just do two. So I'll do something like np delete, and like this is in place or what? I think it returns something. Okay. So sub matrix. Okay, so this is on the row side. So on the row side, I'm just gonna take the row I, right? And then I'm gonna delete, oh sorry, this is row, so row I here, and then I'm gonna give it the matrix here. I get the submatrix row here, and I can then give it, a second, I'm receiving a lot of pings. Okay, now I'm good. I get a submatrix row here, like that, and then I can do it again on the column over here. Okay, and then it's always going to be 0 here, and it's going to be on the column, and that should be good. And I need to kill off the matrix. Sorry, I need to kill off this on this one. Yeah. Perfect. Good. So this, remove the row. This, remove the column. Okay. Then at this point, I should have a 3 by 3. Like right now, we're just gonna print it to see if we're like having a 3 by 3 or not. Let's see. Okay, np. Okay, I have to import it, I guess. True. Now Matt, you forgot. Yeah, I forgot to import Matt. Jesus, Matt. Okay, cool, perfect. So I have a 3 by 3 here, and then this is the next one. Wait, I'm just gonna format this iteration, and then I'm gonna give it the row I and the submatrix here. I'm just gonna use the f string like that. Okay, so iteration 0, we get 6, 7, that thing we killed off. Did we kill off the right one? We have 1, 2, 3, 4. And then in this case, we don't have the 1, 2, 3, 4, it's gone. And then we don't have the 5 here, we don't have the 9, we don't have the 13. This is good. The second one, this should be gone, the 5, 7. Yes, this one is gone, and then we still kill the first row. Okay, so my submatrix is good. Right, at this point, my submatrix is good. So this is my, I will call it a 3 by 3. 3, 3, right? This is my 3 by 3 matrix. And now I can call my determinant here. Right, I call it here. I'm gonna give it a matrix that is 3 by 3. Here it is, and then I'm gonna get that 3 by 3, and I'm gonna print that row. So here we're at row I, right? For for sub matrix for determinant det 3. Okay, let's see if we can get something out of this. Okay, we get a 0 here, 0, 0, 0. Is it normal? I don't feel it's normal that we get all zeros. Yeah, I'm gonna print all of them here too. So okay. Okay, green 1, green 2, green 3. What? Oh, wait, no, I think, okay, yeah, I think I get what's going on. So if I do green 1, I'm gonna get a numpy thing here. Oh, no, I'm good. I'm getting this number, and then this number. Well, like, is this good? I get this big number and then this big number. Okay, and if I do the red now, maybe it's fine. I can't know exactly what the right determinant will be just by looking at the matrix. So this is the reds. They're exactly similar. Okay, that should be good. I think this is legit. Okay, that's done. So I get my determinant, and now the only thing I need to do is just like accumulate these, because if you remember, we're just like summing up like this. I can just accumulate it into like a total det. Here it's 0, and then I just need to do total det equal the total determinant plus, and then this is where I'm gonna do my calculation. I'm gonna do the subdet equal, well, actually subtotal, I would say, equal the scalar times my sign multiplier here times, is it the time here? Yeah, times the determinant of a 3 by 3. And all this is going to give us my subtotal, which I'm just going to add here. And that's that. And after that, I just need to return it. Total determinant. Should be good. Okay. I got two that are good, but I messed up one. Check if you could handle all HKs correctly. Make sure you're handling the input type properly and checking boundary condition. What type of boundary condition? They expected this, and I got. Oh, where am I? Okay. Oh, is it because of the print? Oh, yeah, I'm returning this. They're expecting I think they're expecting an int. So I just need to cast that to an int. Okay, cool. Good. We got it. Nice. Perfect. That was actually pretty straightforward. So I'll just gonna recap a bit here, right? Because the code is not complicated. Like the formula is simple enough. It's just that there's many moving parts here, right? So if I recap the whole thing, I'm gonna recap it here. Okay, here. And then we have our little mess over there. Okay. Okay. So the Laplace expansion formula is recursive. So that means that you're going to do the same thing a multiple time, right? You're going to go and then you're going to do the same kind of iterations again and again. So recursive, well, actually in this case, it was not really recursive. Because we're doing the 3 by 3. If it was a 2 by 2, it will have been recursive. So it should have been recursive here, but what we've done is we are using this formula that is calculating the determinant again and again, right? So we have the determinant for a 4 by 4. This is what we're stopping at, right? And we want to calculate the many determinant that are 3 by 3 because the motion that is about the Laplace expansion is that you're going to kill some of the element like this, and then you're going to calculate the sub matrix, a sub-determinant matrix here. You're going to calculate this, and then you're going to add it, and then you're going to iterate like that. So in order for this to work, you have to encode the sub-calculation of the determinant, the motion that you're going to, and then like the signs that are changing. Because there's also signs here that need to change when you're going to add it together. You see that part? This is encoding this positional kind of thingy here, right? Where like if you're taking this element and killing off this row and this column, this column and this row, you're going to have a plus. And if it's here, you're going to have a minus, right? And this is encoded by just like this little element, this little formula. So -1 exponent row index plus column index, or vice versa. So you're gonna get this type of shape here. So this one will be that one. The scalar a here is just gonna be like which element you're at, and it's two motion. Either you're gonna go like this, right? So you're gonna hop like this, and if you hop like this, what you need to do is you need to set the row to be 0 all the time, and then the column to change, right? The column can move, right? And this J will be the one that will tell you if it's a plus or minus. You can technically do it however you want, but like going through the row or the column is easier because then you just like keep it clean. You have one element that are 0. And then there's like the determinant here, right? And then the determinant, here there's two ways of going about it. We can either go on for a 3 by 3, right? I feel like this is the weakest that you can do, because it's not really recursive if you go for a 3 by 3, because you're literally gonna do, if you look at the code here, right, where we just have a for loop here, and then we're just calling determinant 3 by 3. We're not calling the determinant calculation again on a 3 by 3. You see what I mean? Like it's not calling itself again, it's calling another function, and this other function is just stopping, is just like doing the actual calculation. I think it's fair enough here in this case, because with Cyrus rule we already have a deterministic output, so we're good. And the problem statement was like it's a 4 by 4. So if it's a 4 by 4, you don't need to complicate your life and then have like multiple like function call for the same stuff, because then you're gonna have to make sure that like we're doing this elimination on this submatrix properly, and while keeping in check the pluses and the minuses. It's easier to do it this way, because otherwise it's gonna have to do with the 2 by 2, and then you're gonna stop right when you hit like this type of matrix. And in this case, you're gonna do this times that minus this times that, right? This is the normal like 2 by 2 formula that we have over here. But this we decide not to do. So we selected that one over here. So we're good with that. And that's it. And the only thing that you need to encode then is like, in our case, we decide to move in this way, right? From here to here. So the first element will be 1, right? Second element will be then 5, and then 9, and then 13. And remember the minuses, so this is going to be a plus. This one will have to be a minus. This one will be a plus. This one will be a minus. And then once you're going to create the actual matrix, you're going to kill off, in this case, you're going to kill off this and that, right? And then on the second iteration, you're going to kill this and that. And then like the remaining will be your matrix that will calculate the determinant on. And here is going to be this and that. And then you're going to calculate this and that. That's the motion we encoded here, right? So this is the Cyrus rule, easy. And then this is everything that I just said. I decided to make a NumPy array here. Otherwise, we'll have to re-implement like index, like slicing on the on list of lists, and which is absolutely useless. There's no point in doing that. So we decided to do it in a NumPy array here, and we could just slice it like that, and we're good to go. And that's it. That's pretty much it for today. I hope that was useful. And if you're watching this afterward, don't hesitate to check out this little website. I think it's pretty cool, honestly. Like a lot of cool problems, and there's a lot of them. Like there's some of them that are in, let's say, pure machine learning here. There's some of them that are in pure deep learning. There's some of them like in NLP, statistic, probability, and they're pretty well made. There's some of them that have some bugs in it, so watch out for that. But others are pretty good, and it's open source, so people are actively, submitting problems. So if you think about something, you can submit it there. I'm gonna leave the links right here if you want to test it out. Generally, I recommend like people to start to play around a bit with the coding aspect, even if you're very like a early beginner. Do start to kind of remove the abstraction of the maths and start to kind of actually program, get your hand into programming. This is still fairly deep at the deep level, right? I would move quickly up into a more practical realm, let's say, with the library that are abstracting a lot of stuff for you. But if you're actively studying things like math for machine learning, right? Go ahead, try to supplement a bit with this. It's fun to read this type of stuff, right? But once you implemented it once and then you understand a bit the motion, it removes a lot of the uncertainty around like what is this formula about, how it moves, right? So by doing the coding at the same time, by trying to get your hands on it, doing the exercise also like at the end here, you get an idea of the motion it's going through, the mechanic, and it removes a lot of the anxiety, I would say, about this whole thing. So I hope that was useful, folks. I'll see you in a next video. I'll maybe do another one of these live stream in the weekend. And I wish you all a great rest of the day.